Okay, so this is going to be a very short video, and what I want to do is prove not directly related to the questions in the prior couple of videos, related to the Vitali kind of construction and exist non-measurable set, the existence of a nice measure on all real line, but it's still kind of neat, and it's a very natural question. And the question is, can you do better than Lebesgue measurable sets in the sense that is there a larger collection of sets where Lebesgue measure is really nice? And the answer is no. And it's actually not hard at all to prove. With the following theorem, essentially maximality of Lebesgue measurable sets. So let's say M prime is a possibly larger um, now let's say it's a sigma algebra such that all the niceness we need is the following. A B disjoint um, basically finite additive. So these are disjoint, but they equal the empty set. All right. And this here, to be clear, is Lebesgue measurable sets, as usual. So yeah, so let's say we have a possibly bigger, nice collection of subsets in the sense that Lebesgue measure is finitely additive on n prime. Then the conclusion is, well, it's not bigger. Um, they have to be same. They coincide. So basically, this m prime is Lebesgue measurable. So there is no bigger collection of subsets of the real line where on this bigger collection, Lebesgue measure is um, uh, finitely additive. And I should be careful here because we're assuming this is bigger, it might not be Lebesgue measurable. So we're only dealing with Lebesgue outer measure on a M prime. Okay. How do we? So again, this is just kind of neat. I mean, it's a very natural question, and it has a surprisingly straightforward answer, and the proof is pretty straightforward. Um, or rather, the surprising is to me the proof is so straight. So let's say E is an M prime. Okay, so for each N, natural number N minus N to N, obviously it's a big measurable, and that means it's an M prime. That means for each N, En equals E intersect minus N to N is an M prime. Okay, I don't, I think I do this in one of the videos. I don't remember. Actually, probably not because I put it as homework. But what you can do is you can pick yeah, pick G pick a G delta set G n is contains En where this is true. Remember, this does not require measurability. If you want Gn take away En be measure zero, that's equivalent. The existence of this Gn is equivalent to En being. We don't know that because all we know is E is in this possibly bigger collection of subsets of E. No matter what, measurability or not, we can always do this by basically a definition of outer measure. Right, so we have a sigma algebra. So in particular, Gn is an E M prime because, well, it's G delta, so it's certainly a big measurable. So that implies Gn take away En is an M prime. Again, we have a sigma algebra, and sigma algebras are closed under set differences. Okay, so what does that mean? Point is I can write Gn as Gn take away En, disjoint union En. Both of these are in script M prime. And that means the big outer measure of Gn is going to be the big outer measure of Gn take away En plus the big outer measure of N. Um, right. But this here is measure zero. Uh, yeah, right. So this, so the whole point of this is we want this to be finite, right? We want to kind of somehow use excision property. Well, we don't really have it without measurability. That's kind of it. We want to avoid using measurability to prove excision. That's essentially what we're doing. So this equals the outer measure just from here of Gn. Outer measure of En is finite, it's at most 2n. So that implies finally that this subtract both m star of Gn from both sides. That means this is zero, and that's good. Why? Because what do we know about sets of measure zero? They are measurable. Gn take away En is Lebesgue. All right, so finally, because Gn contains En, you can write En and you can draw a picture or just do one as a subset of the other. It's easy. Gn intersect Gn take away En. Well, so this is Lebesgue measurable, so this is Lebesgue measurable. We had Gn is Lebesgue measurable because it's a G delta set. All right, so each En is Lebesgue measurable. And so that means E is Lebesgue measurable, kind of the obvious reason. And right, so E is the union of the ENs. Each one of these is measurable, Lebesgue measurable, so E is it. Yeah, remember the whole point was that if I didn't intersect with something finite, then I would not be able to subtract both of these because we're, subtraction by infinity on both sides of the equations. We just don't define that. So this is why we need to do this EN trick, as we've done many. We need E to be the union of, doesn't have to be disjoint, but we need E to be the union of countable union of finite measure sets, or finite outer measures. All right, so yeah, again, surprisingly easy proof. Hopefully this was interesting. So long, take care, bye.